Alright, this is the last chapter, chapter 14, where we're just going to have a little discussion about what to do when data is not normally distributed, or I don't know if it comes from a normal distribution. If you look at these samples and their histograms, can you really tell whether or not it comes from a normal distribution? You could say, yeah, maybe this one, it has sort of a crest in the middle, there might be some sample effects here that made me miss that. Maybe this one, I don't know. You really can't tell visually. And we've avoided that subject, and for good reason, because it can get fairly complicated. And we're still going to not really address it in this chapter, but I just want to be aware of things you can do if your population is not normal or you don't know. Let's look at a very simple example, college major example. So one thing I can do is transform my data to be more normal, so to speak. And then I can go back and use the tests and the techniques that we have developed and discussed. So my variable is the major, English versus history, and I am looking at the number of CDs listened to within the past week. So I have two, just for the sake of example, I have history majors and English majors. And I have a sample of 4 here, number of CDs listened to, giving me a mean of 9.5, and I have here a sample 36, 9, and 0 and 9, number of CDs listened to. So if I look at, now the samples are really small, yes, if I look at what the samples suggest, I see this sort of this little breakdown here, this little histogram sort of diagram here that may or may not be normal. This one is not normal just based on a visual assessment, because I have this value here of 36 from a sample of 4. I don't know what happened here. One thing I could do is a square root transformation. So all I'm going to do is I'm going to transform the numbers that they sit more in a bell curve shape. That's all. The numbers still have their own identity, so to speak. I'm just going to take the square root so that the numbers sit in a formation that looks like a bell curve. So I take the square root of these numbers and I get 2433. And you see, yes, not a big sample. You see the little normal shape being resembled more than it has there. This one wasn't bad either, to be fair. For this one, I take the square root and I have them clustered together much better than before. So it sort of just has a scaling effect, getting everything together in a shape, in a distribution that resembles a normal distribution more closely, that I can then use known techniques for. So if I have a skewed distribution before, a square root transformation could make it look like a normal distribution. And I'm not changing the information, I'm just making them look different so I can use my techniques. I can easily go between these by way of my square root. So when I look at another example, I'm looking at the results of a study comparing highly sensitive to not highly sensitive children on the number of books that they read. So highly sensitive, yes, and no, I have some sample values again with a mean and a standard deviation. The square root transformation gives me this in this table. And I can now conduct a t-test on this for independent means using not the original format of the data, but the square root transformed format. And same as before, I get my pooled variance, the difference, t-score, and I see that I can reject the null hypothesis. So if my data originally doesn't come from a normal distribution, I can transform it and I get a normal shape which I can apply the t-distribution to. Let's go back to our college major example, and the second option we have for transforming data to be able to work with it is rank ordered transformation. So I again have the history majors versus the English majors. Now what I'm going to do is I'm going to rank all of these numbers, all 8 of them, and I get that 0 is the first number, the lowest, from lowest to highest. I'm going to rank them. And then I have a 4, that's going to have rank 2. Then I have 4 9s. So they're tied for ranks 3, 4, 5, and 6. I just get an average rank among those numbers, which would obviously be 4.5, and give them all that rank. And then I also have a 16 and a 36 for rank 7 and 8. So I'm just ranking all the numbers. Duplicate numbers get an average rank. Let me just see if I have everything. Now, without discussing too much detail, we're just giving a taste so that you're aware of everything is not following a normal distribution, that there are things that you can do if you're ever faced with something like this. We're not doing these in incredible detail. I just want to be aware of them. And by way of SPSS, we can easily run these tests. So we're aware that we're not looking at these in a lot of detail. There are rank order tests that you can conduct after this transformation, depending on what I wanted to do. If I'm looking at the t-test for dependent means, but I didn't have a normal distribution for my population, I used the rank order transformation. I used the Wilcoxon signed rank test. A t-test for independent means, I can use a slightly different test, or the Mann-Whitney U-test is also very common. If I wanted to perform an analysis of variance, the Kruskal-Wallis H-test is the common one, and a Pearson correlation, Spearman's rho is the common one. Now again, we're not looking at these in a lot of detail. It's just something that I want to be aware of, that things aren't always as nicely boxed as we've had up to this point when things are not normally distributed. So just as a very brief example, I know after this it might not be incredibly clear how to actually perform these tests. You can look at the book, and even then it's just so that we're aware of it. If we're looking at the Wilcoxon rank sum test for the study of books read by highly sensitive versus not highly sensitive children. So remember, what does that now replace in a way? The t-test for independent means. So I have two separate groups trying to see, are their means different or the same? So I'm ranking all of them, and then I can look up, there are tables, that tell me for the significance level what kind of cutoff value do I have, and then I compare that to the cutoff value, the sum of all the ranks of the group sum of the ranks of the group predicted to have lower scores, 11 equals, but does not exceed the cutoff for significance. And then I can decide to reject or the null hypothesis. Now, again, I am avoiding the detail of this because it's slightly outside the scope of what we're doing. I just want to be aware of two transformations, the square root transformation as well as a rank order transformation. And you look in the textbook for more detail, but it is outside of the scope for this course. If it's interesting that you could still perform a t-test, in this case for independent means, using the ranks, excuse me, the ranks instead of the raw scores, and your results are actually not bad. So here you get the ranks like before. You take the mean, the pooled variance, everything the same as if this was your two sample sets. You get a cutoff depending on your alpha value, and you'll find that the conclusion is similar to the more complicated rank sum test that we haven't really discussed. Now, in an actual research study, you'd have to be aware of the more correct procedure, but take note that looking at the ranks, you can still perform a t-test or whatever test you want as if it was a normal distribution, and the results are fairly comparable.